Hi everyone and welcome to this episode of Keipert Labs. In today's video we're going to be discussing collision theory, the fundamental principles behind how particles are able to undergo chemical reaction, that bonds are able to be broken and reformed based on particle collisions. So firstly we're going to look at the fundamental principle that reactions require particles to collide in order for chemical change to occur. And we're going to then look at what we call the Maxwell-Boltzmann distribution, looking at the behaviour of moving particles. We're looking at the relevance of what we call molecular orientation in a particle collision, defining what we mean by activation energy, and then looking at four main factors that affect reaction rate based on our understanding of collision theory. So reactant concentration, surface area, temperature, and the presence of a catalyst. So firstly, one of the fundamental principles behind chemical reactions is that in order for a reaction to occur, the particles must collide. We can't be rearranging atoms and reconnecting things if the particles are nowhere near each other in the physical universe, in the space of the container in which they are. If they're not in the same beaker or in the same box or in the same room, then there's no way that they can be rearranging with one another. Okay? But one of the things that is very relevant here, and we're going to unpack a little further, is this idea that yes, we need particle collisions, but not all particle collisions result in a chemical reaction. That sometimes the particles bump into each other and nothing changes. And we're going to look at why that is. But in order for the collision to actually cause a chemical reaction, we need two kind of main things. Firstly, we need it to be sufficient energy in that collision, and also we need the right molecular orientation. And we're going to unpack what those two things mean. But you can see here in this image this idea of forming water from hydrogen and oxygen gases, that the particles need to approach each other, that when they collide that we form this kind of middle ground, what we call an activated complex, where all the bonds are kind of in the process of being broken and then about to be reformed, and then as they reform we produce our product particles. Okay? So now here we have what we call the Maxwell-Boltzmann distribution. Now, so this is a graph of kinetic energy of particles in a substance with their abundance, like how many particles have certain amounts of kinetic energy. Because the thing is that we talk about, particles have kinetic energy, and we talk about it in relation to temperature, and this idea that temperature is a measure of the kinetic energy of the particles in a substance. But the thing is that not every particle has the same amount of energy. In fact, there is a wide range of kinetic energies that these particles could have. So what we're saying is that some particles will only have a tiny bit, some particles will have heaps, but more commonly that we end up with an average amount of kinetic energy. And that average is what we are quantifying as temperature. Saying, all right, well, we're not focused so much on the extremes. We're saying once we look at all the particles, what's the average amount that a particular particle might have? So you can see it's not like like a bell curve. It's a bit like that, but we have this kind of this long kind of tapering section as the kinetic energy increases. Okay, but we do have an average around about this peak over here. Okay, but what that means, and this is what we're going to come back to, is that only a small proportion of the molecules that make up this curve have a high level of kinetic energy. Most of them have a fairly kind of middle to low amount of kinetic energy, but as we work our way up here, the amount drops off quite a lot. Okay, so we talked about the fact that a collision needs to have sufficient energy, and we're going to come back to that Maxwell-Boltzmann distribution, but we also need the molecules to collide in the right way. That is, the molecular orientation needs to be in a way that is allowing those bonds to rearrange. So if you look at the image here for this reaction of A with BX, for B and then forming B and AX, that we can see that in this situation that if the A approaches from this direction and hits the B, it's not going to result in a reaction. Whereas if an A approaches from the other side and hits the X, we will get an effective collision that will cause rearrangement. Okay, so the idea that particles must be facing the correct way or must be facing a specific way for that collision to result in a certain outcome. It's a bit, really, one thing you can picture this is like cars having an accident. It's like depending on which way the cars are facing, which direction that they're traveling, where the collision actually occurs on the cars will cause a very different outcome. A head-on collision versus a rear-ender collision versus a T-bone, where one car hits the side of another car. Does it hit at the front? Does it hit at the back? Does it hit on the doors? Left side, right side? All of those lead to different outcomes. And so picturing it the same sort of way, that the way that the molecules actually interact in this collision makes a huge difference to whether any change will actually happen, because this particular arrangement facilitates the breaking of bonds and the formation of new bonds. So it needs to be in a way that will allow the new bonds to form at the other end. Okay? But so now we're going to come to this concept we call activation energy. So we're saying, all right, well, that the collision needs enough energy for the rearrangement of bonds to actually happen, that they need to collide in just the right way. But what we're saying is that there's kind of an amount of energy that collision needs to have before it will actually work at all. And if it doesn't have that amount of energy, then it won't happen. And we call that the activation energy. That is, this is the energy required for the collision to result in a reaction, as long as the orientation is right. Okay, if you have the right amount of energy but they're facing the wrong way, it's still not going to happen. But this is the amount of energy that's needed for that collision to actually be successful. Okay, and we give it the symbol of E with a little subscript A. So EA is activation energy, energy of activation. Okay, if we're looking at a diagram here, energy profile diagram, this amount of energy is the amount that we have to put in for the reaction to be working. Okay, because the idea is that I imagine it like you're riding a bike over a hill. You have to be able to get to the top of the hill to be able to roll down the other side. If you can't get there, then you go backwards and you don't reach the end. Okay, but as long as you have an amount of energy, as long as you're able to get to the top of the hill, only just or with lots to spare, then you roll down the other side freely. Okay, and so this distance, this amount, is the specific activation energy. So here, if we look at this, we're talking about 58 kilojoules of energy to go from 45 up to 103. Okay, and so that, yeah, unless you can put in that much energy in that collision, it's not going to happen. All right, so it's kind of like a threshold, that unless you pass that threshold, that then it's not going to work. Okay, but so now if we come back to our Maxwell-Boltzmann distribution, where we're looking at the actual amounts of energy that the particles have, then that means that we can actually draw this as a threshold on this graph and say, all right, well, unless the kinetic energy is greater than that value, because that's the only place this energy is coming from for them to actually cause a reaction when they collide, that it's just making the particles move enough that when they bump into each other that it works. So unless the kinetic energy is greater than that value, that collision will not cause a reaction. So any of these particles down here that collide are not going to cause a reaction, only ones that have this value or above. Okay, so you can see that only a very small proportion of all the particles in that substance are capable of reacting at any one time. Okay, so you've got to have kinetic energy greater than the activation energy for a successful collision. So now we're going to have a look at the 4 factors that are that based on our understanding now of collisions, that influence reaction rate. And the first one is reactant concentration. That is, how many particles of that reactant do you have in the space that you've got, whether it's water or it's a gas or whatever. If you have a low concentration, you don't get as many collisions, okay, because there's fewer particles that could possibly interact. The more particles you have, the more possible collisions, the faster reaction will happen in terms of, how many moles per minute, for example. Okay, so more particles, more collisions, therefore we get a faster rate as we increase our concentration. Well, what about now temperature? Because we said that temperature is a measure of the average kinetic energy of the particles in a substance. So that means if we increase the temperature, then we're increasing the average. And then if the threshold is the same, that then more particles will be past the threshold. And that's what we see here, is that if we look at these 2 curves, we've got this average here for at the lower temperature with the blue dotted line, and this is the average for the red temperature, the higher temperature. You can see that the curve has shifted further up towards the right. That is, more particles have higher levels of kinetic energy. And if we look at our dotted line threshold, our activation energy, we have a larger number of particles that meet that criteria, that they're already past that point. So therefore, more particles with activation energy, therefore we have a higher, faster rate. Okay, so the higher the temperature goes, the faster the rate is, and the opposite is also true. If we cool it down, reaction happens more slowly. Okay, looking at surface area now. Okay, so if I want you to imagine that we have the blue and the red are reacting particles. In A, you can see all the blue particles are stuck together. In B, they're clustered into smaller chunks. The idea is that when we increase the surface area, when we break up the substance into smaller pieces, there are more physical places for those particles to interact and collide with each other. Okay, if we look at the one on the left, all of these blue particles in the middle can't physically touch a red one to react. Only the ones on the edge can. Once they react, then the inside bit is more exposed and it can react, and then so on and so on. We notice this with magnesium reacting with acid, is that the outside reacts and then it kind of starts to wear away, and then the next bit can react and the next bit until eventually it's all reacted, if you've got enough of the reactants. But if you break it up into pieces, that reaction is so much faster because every little bit is more exposed, more collisions, more accessible, so more collisions overall, and therefore you get a faster rate with greater surface area. Okay, and the last thing we're going to talk about is the presence of a catalyst. So a catalyst is an additional substance that does not get used up in the reaction, that its job is to reduce the activation energy needed for the reaction to occur. So it's like, you know, if you're trying to ride your bike over the hill, it's like going an alternate shortcut that is a shorter hill that will still get you to the same destination, but with a much easier to get over the hill to start with. Okay, so if we look at this diagram over here, you can see the hill is shorter. This kind of purpley red one is without a catalyst, the blue one is with a catalyst. You're still getting to the same outcome at the other end, but it's a lot easier to get it started. If we look at our Maxwell-Boltzmann distribution, that we've shifted that activation energy threshold, so we have more particles that are past the threshold by this alternate pathway. Okay, more particles with energy greater than activation energy, therefore the rate is faster. Okay, so the idea is that we don't get more of the reactant as a result of the catalyst, but we do get more in a given time frame. You know, it might take you a much shorter time to get the same amount. And so depending on the context, that's very, very relevant. Now we are going to look into more detail about how a catalyst actually functions in a subsequent video. So you'll get a bit more detail to actually see, right, well, how is it physically able to actually do this? But the idea here is that now you can see that it helps to increase the reaction rate. Okay, so we've looked at this fundamental principle about particle collisions in chemical reactions. We've seen that particles have a range of kinetic energies that we can graph on the Maxwell-Boltzmann distribution, that the molecular orientation during a collision makes a huge difference as to whether a reaction will occur. We've seen activation energy as this minimum amount of energy needed in that collision for the reaction to happen. If we don't have that, it won't work, and we've given it a symbol of EA, and we've seen the effect of these four factors on reaction rate: concentration, surface area, temperature, and the presence of a catalyst. Thanks very much for watching. Bye for now.